Okay, so the third case of exponential growth that we're going to be going over is logistic growth. As you can see, the growth is also growing in this one. This comes from the differential equation y prime equals ky times a minus y, and this causes the rate of change to scale both proportional both to y and a certain constant minus y, and we call this constant the carrying capacity a. Well, sometimes it's c, but we have c elsewhere in the solution. So the solution to the differential equation is a over 1 plus c e to the negative akt, and c is it's just a constant that tells you how many members of the population are present at times t equals 0, because of course at t equals 0 this exponent cancels out, and k is again the rate of growth. And as I mentioned earlier, at t equals 0 we have a over 1 plus c, because this exponential factor cancels out because of this t in the exponent. Okay, let's quickly solve a problem. Oh yeah, I'm not going to go over how to derive the solution in this video because it's kind of long and I don't have that much time, but I will say that it is in the Barron's book under example 20, I believe. And also, so we generally use logistic growth for things such as population growth, as I mentioned earlier, where there's a limiting factor such as food or space or something. Like, for example, the number of penguins on an iceberg could be modeled by a logistic growth function. You could also use it for the stuff like the spread of a disease, or the spread of a rumor, or a religious cult, or I don't know, the rate of the number of reactants on the side of a certain chemical equation. But anyways, here's the problem that we're going to be going over. Okay, it says the number of squirrels in a squirrel population cannot exceed 1,000, and the population grows at a rate that is proportional to both the existing population and the maximal attainable population. 2 years ago, the number of squirrels was 1,000, and 1 year ago there were 400 squirrels. So here we have a equals 1,000, y0 is 100, and y1 is equal to 400. So how we're going to solve this is we're going to solve for the constants in the logistic growth equation by plugging in the preconditions. And as I said earlier, when t equals 0, y is equal to a over 1 plus c. So here we have y0, which is 100. Y0 is 100, which was 2 years ago, is equal to 1,000 over 1 plus c. And this is pretty easily solved. You end up getting c equals 9, because 1,000 divided by 10 is equal to 100. Alright, so now we plug in the second precondition and this c to solve for k. And so we get the 1 year ago it was 400. 400 is equal to 1,000 divided by 1 plus 9. Whoops, 9e to the negative ak. And of course t is equal to 1 here, so we'll just leave it out for now. Solving for this, we get, if we divide both sides by 1,000 and then take the reciprocal of both sides, we get 5 halves equals 1 plus 9e to the negative ak. We subtract 1 from both sides and divide by 9. That's 3 halves divided by 9, which is 1/6. And we get 1/6 equals e to the negative ak. We could solve for k here by taking the natural log of both sides and dividing by negative a, but we're just going to leave it this way because this expression actually appears in the original equation for logistic growth. Okay, and now the final step is of course plugging in the t that we want to solve for, and so we have y2 is equal to 1,000 over 1 plus 9 times 1/6, and this is where the e to the negative ak comes in. We left it in that form so we can just write 1/6 here rather than having to write e to the negative 1000 times whatever the k is, and then t is equal to 2, so we're just going to raise this to the power of 2 because of the properties of exponents. Okay, so this is pretty easy to solve. 1/6 squared is 36. 36 times 9 is 1/4. 1 plus 1/4 is 5/4. 1000 divided by 5/4 is equal to 4000 divided by 5, and we get y2 is equal to 800. So there are 800 squirrels this year. Okay, so that's just a simple example of how to use logistic growth.